In this video, I want to talk about Ampere's law, which is definitely more complex than Gauss's law for magnetic fields. So what this is saying mathematically is that if you pick any point in space and you take the curl of the magnetic field intensity at that point, it will be equal to the current density at that point in amps per meter squared plus the rate of change of the electric flux density at that point. Now, I want you to recall the definition of curl, which essentially it is circulation, or H dot dl, per really small loop, or circulation per meters squared. And it's equal to this. Now, I want to take this equation and I want to explain it precisely in words that will, I think, help break down what this is really saying and give you a more intuitive understanding of it. So I know this is a mouthful, but bear with me and let's work through this. And I think if you pay close attention, it will really help you get a better grasp of what Ampere's law is saying. Okay, so what it's saying is that if you pick any point in space, so at any point in space, the circulation of H along a really small loop wrapped around any, it can be x hat, y hat, z hat, theta hat, r hat, whatever, any unit vector divided by the area of the loop, so a really tiny area, is equal to the current density in amps per meter squared in the direction of the unit vector plus the time rate of change of the d field in the direction, in the direction of the unit vector. So I know that was a mouthful, but what I'm saying is that, again, you pick any point here, and you can pick any unit vector, let's say r hat, and then if you sketch a small loop at that point, and then compute the integral of h dot dl, the circulation, and then divide that by the area of this loop, then that will be equal to the current density in amperes per meter squared going in this r hat direction, plus the rate of change of the d field, in particular in this direction. What do you want? What do you want? Oh, I see. Chicken? You want chicken? Oh, yeah, you want chicken. So let me give you a mathematical example. Okay, suppose we've got a point P here, and what we do is we measure the H field at that point, the current density J, and the electric flux density at the point as well. And we measure them, and let's say they're these values, and they are a function of time. So what Ampere's law tells you is it tells you the circulation of the H field around any unit vector. It could be x hat, y hat, z hat, doesn't matter. Let's go ahead and choose x hat for an example here. And we can go ahead and form a small loop that wraps around and is perpendicular to x hat. And we can calculate the circulation, or h dot dl, around this small loop. And the direction that we go around can be determined by the right-hand rule, where your thumb will point in the direction of x hat and your fingers will curl in the direction of the circulation. So then what you can do is if you were to calculate h dot dl for that small loop and then divide it by its area, so cx would be the circulation around the x hat vector there, divided by delta y delta z, which is the area. And then if you were to take that limit as delta y and delta z go to 0, because that's the whole idea of the curl, that would be equal to the current density in that direction, in the x direction, plus the time rate of change of the d field in that direction as well. So here jx, you can see the x component of j is 3, so that'll be 3, plus the time rate of change of dx, so the x component of d is 2 squared, so you take that derivative, it's 2 times t, so plus 2 times t. So this is what Ampere's law is saying. Now the cool thing about this is that you could go through this same process except for the different unit vectors. So you could do the y hat direction and you could do the z hat direction. So the y hat direction, you'd find the circulation of a loop that wraps around the y hat vector, and then divide that by the area of the loop, which is delta x delta z. Then as you take the limit of that as delta x and delta z go to 0, it would just be the y component of the j field here, so it's 1 here, or not the j field, but the current density, so 1, plus the time rate of change of the field here in the y direction, 2t, so that would just be 2. So you add those together and that gives you 3. And you can do the same thing for the z direction. So you get three different numbers, or 3 different circulations per small loop. So we can put all of this together and actually form a vector with all these separate circulations per small loops, and set the x1 with an x hat component, the y with a y hat component, and the z with the z hat component. And this is our definition of curl. So if you set this as a vector and then take the limit as these approach 0, this here will equal the curl of h. So then you can plug and chug with the numbers we got, and this here is the value for, or the vector for, the curl of h. So before I end this video, I wanted to take the time just to clarify 2 things that I thought that could be maybe a potential source of confusion. One is that I sketched this loop here, and I probably should have sketched it to where this point here was right on top of the point P here. That's what I meant to do. The small loop you sketch out should always be right there at the point. Another thing I want to clarify is that here I gave you different values for h, j, and d. And this was for a specific point in space. So this is after you plug in values for x, y, and z, and then assuming this is what you have there. And so then it is a function of time, but with these values I'm not specifying how they are functions of x, y, and z. And if you wanted to calculate like this circulation value, the cx value, you would need to know how the field varies as a function of distance. But I didn't actually give that information to you here. This is just an example just to show you how it works. In reality, if you wanted to calculate the circulation, you need to know how these quantities vary as a function of x, y, and z. But I just wanted to clarify that. So in my next video, I will talk about the integral form of Ampere's law. We've been focused on the differential form, looking at what it means for a specific point in space. But turns out we can apply Stokes' theorem to Ampere's law, and we can then use the integral form to apply it to all sorts of really useful problems. So thanks for watching, and I'll see you in the next video.